Today we're going to start out by defining acids and bases as three historical figures have done, and then we're going to start working with the idea of what sorts of things are acids and bases and explore how we can tell whether an acid or a base is stronger or less strong. This will sort of set the stage for material to come in subsequent videos. The first definition that we have historically is from Svante Arrhenius, who's a Swedish chemist, and he came up with the first definition of what an acid and a base is. According to Svante Arrhenius, an acid is something that yields H3O plus ions. These are called hydronium ions when they're in an aqueous solution. These are often modeled as H plus ions. And you're going to often see me not write H3O plus, but H plus. And bases, according to the Arrhenius model, are substances that when you dissolve them with water give OH minus ions. So an example of an acid would be something like HCl. HCl would react with water, this is what really happens, and it would produce H3O plus, the hydronium ion, and leave Cl minuses behind. Now, I'm going to net the water out, and quite often when I do this, I'm going to take water from both sides, and I will instead model this as HCl simply decomposing into H plus Cl minus. In all the calculations that we're going to do in this chapter, if you just substitute H3O plus for H plus, you will get exactly the same value. Here's what might be considered a base. Something like sodium hydroxide, which is an ionic compound that breaks up, just dissociates in water to yield the OH minus, would be considered a Arrhenius base. The definition of acids and bases got refined a little bit and expanded slightly by two chemists that were working independently of each other, Bronsted and Lowry. So the Bronsted-Lowry definition is that acids are proton donors and that bases are proton acceptors in chemical reactions. This eliminates the need to actually see OH minus ions produced by a substance. This expanded the definition of what an acid and a base was because it included everything that Arrhenius thought was an acid and base, plus some other things. This is an example of a Bronsted-Lowry acid-base reaction. If I have ammonia, which is considered a Bronsted-Lowry base, and I react that with HCl, the first thing that will happen is this strong acid, the HCl, will donate that proton to the ammonia. And so that will make NH4 plus because the proton is positively charged. And then that will leave behind Cl minus. Now this is an ionic compound, NH4Cl. That's the end result. But the donation of a proton and the acceptance of a proton is what makes hydrochloric acid and ammonia acid and base in the Bronsted-Lowry definition. This is the definition that we're going to sort of work with the most. The most modern definition of an acid comes from G.N. Lewis, the same person who gave us Lewis structures and dot notation. The Lewis definition of an acid is that it's an electron pair acceptor, and bases are electron pair donors. And this includes the things that we consider acids and bases in the Bronsted-Lowry definition. For example, in that last example, we had NH3, and this is a Lewis structure for NH3, and this was reacting with HCl. So H bonded to Cl. Now the hydrogen broke away by itself and made an H plus, which has no electrons. That H plus accepted this electron pair when this bond was formed to make the NH4. So that made the H plus here an electron pair acceptor, and the ammonia was the electron pair donor in the formation of that bond. When both of the electrons that are used to form a bond come from the same atom, like is the case here, that bond is considered a coordinate covalent bond. And coordinate covalent bonds are always formed in Lewis acid-base reactions. Another example of a Lewis acid-base reaction would be the reaction of BF3, so boron with 3 fluorines, boron trifluoride. And remember, with boron, you only need a full sextet, so I don't need an electron pair there. I shouldn't put one. And then fluoride ion. Fluoride ion has a full octet and carries a 1 minus charge. When this reaction forms BF4, boron tetrafluoride, that bond, that additional bond, was created from the lone pair that came from fluorine. So fluorine is an electron pair donor. That makes it a base, the fluoride ion. And the BF3 was an electron pair acceptor, so that makes it a Lewis acid. Lewis acid and bases, I'm just introducing them because you do need to know what they are, but we're probably not going to work with that definition nearly as much as we will with Bronsted and Lowry's. The Bronsted-Lowry definition makes it possible for us to think about conjugate pairs. In an acid-base reaction, you'll have 2 species that will differ only by 1 proton. They'll be on opposite sides of the arrow, and that's called a conjugate acid-base pair. Like, for example, if I were reacting acetic acid, which is HC2H3O2, with water, I would end up getting hydronium, H3O+, and acetate, C2H3O2 1 minus ion. This is an acid. The species on the right-hand side that differs only by 1 proton is the conjugate base. So this is a pair, a conjugate acid-base pair. And the same thing is true for water. Water is a base, and there's a species on the other side of the arrow that is its conjugate acid. It differs only by a proton. The conjugate acid has 1 more proton, and the conjugate base has 1 less proton. That's how you can spot them. What are the conjugate acid-base pairs in this reaction? Well, if I look here, I see HCO3 1 minus, and on the other side I see H2CO3. This is a base compared with this, which is the conjugate acid. H2CO3 has 1 more proton, so it's the acid, and HCO1 minus has 1 less proton, so it's the base. H2PO4 1 minus has 1 more proton than HPO4 2 minus, so that makes it the acid to HPO4 2 minus, which is the conjugate base. What are conjugate bases for these things? Well, you can find conjugate bases even if you aren't in reaction by just taking a proton away. If I remove the H plus from HI, I end up with I minus. If I remove 1 H from HPO4, I end up with H2PO4. Now notice that the charge is dropping by 1 when I do this because I've removed a proton, and protons are positively charged. NH4 plus. Here the H's don't come in the front of the formula, but the process is still the same. I reduce the number of H's by 1, and I reduce the charge by 1, which makes NH3 neutral. Water. We don't typically think about this as an acid, but it is. Conjugate base would have 1 less H. Thinking about water as HOH, I'll just take that H away. So OH with a 1 minus charge, the hydroxide ion, is the conjugate base for water. We could repeat that exercise by finding conjugate acids. Now I'm going to add a proton, so the charge will have to go up by 1, and the number of H's will have to go up. So the conjugate acid of water is H3O 1 plus. The conjugate acid of the sulfate ion is HSO4 and now 1 minus, not 2. The conjugate acid of HPO4 2 minus is H2PO4 1 minus, and the conjugate acid of PO4 3 minus is H1PO4 2 minus. Here's an example. Water and HPO4 2 minus that can be an acid or a base. Substances that can function as an acid or a base, depending on what else is going on, are called amphoteric substances. Amphoteric substances can be acids or bases. An example would be the bicarbonate or hydrogen carbonate ion, HCO3 1 minus. If you put this in the presence of a strong acid, it will accept that proton and function like a base to make carbonic acid. If I take that same bicarbonate ion and I put it in the presence of a strong base, it'll donate a proton and form water. And then you'll end up with the carbonate ion, CO3 2-. So bicarbonate is an amphoteric substance. Sometimes it's an acid, sometimes it's a base, depending on what else is present. Let's talk a little bit about how strong acids are. The strength of an acid is really a measure of its ability to donate protons. Something that can donate protons better is a stronger acid. In this equilibrium reaction, equilibrium is reached when you still have mostly still reactants. Very little product, very much reactant is present at equilibrium. So that means this reaction lies mostly to the left. That makes this acid the stronger of the two acids. Our two competing acids are acetic acid and hydronium ion. Because at equilibrium you have primarily reactants present, acetic acid isn't a strong enough acid to overcome the H3O plus and donate protons to water. H3O plus is much better at donating protons to the acetate ion. And by the same token, the acetate ion is a stronger base than water because it's better at accepting protons. Here's something that's true about weak acids. The stronger an acid is, the weaker is its conjugate base. So H3O plus is the strongest acid. Water is the weakest base in this pair. Strong acid means weak base. The weakest acid is acetic acid. The strongest of the two bases is its conjugate base. Some acids are considered absolutely strong acids because they ionize completely when they are placed in water. There are only 6 of them, and this is a list that you should know. One of them is hydrochloric acid, HCl. We're very familiar with that one. Sulfuric acid is H2SO4. Nitric acid is HNO3. Hydrobromic acid is HBr. Hydriotic is HI. And perchloric acid is HClO4. That list of 6 acids, the most common ones are HCl, H2SO4, and HNO3. Those completely ionize, and so every molecule of any of these acids will be completely converted into ionic products, H pluses and an anion. This is a way of visualizing the difference between strong acids and weak acids. On the left-hand side, we have a strong acid. H's are the little blue spheres in here, and the anion from the strong acid are the larger purple spheres. In this beaker, which is supposed to sort of visualize what you could see, if you could see things on the atomic scale, you don't see any molecules anymore. Every HA acid molecule has been completely split up to H pluses and A minuses. On the right, we see what a weak acid is like. There are some H pluses in here, and there are some B minuses. That's the anion for this weak acid. But primarily, you see still HB molecules. That's mostly what you see. And so in this reaction, when HB is put in water, it reaches dynamic equilibrium with H pluses and B minuses. And in fact, mostly you still have HBs when you reach equilibrium. If you're trying to compare acids and want to know just in general, how can you have a gut feel for which is going to be the strongest acids, we have a few trends in the structures and the periodic table positions of parts of acids that can help us determine acid strength. First of all, thinking about binary acids contain only hydrogen and another element. We'll define them formally later. The strengths of binary acids increase from the left to the right. For example, water is a very weak acid compared with HF, which is stronger. It's not an absolutely strong acid, but it's stronger than water. Why would that be? Well, this is explained by differences in electronegativity. If I look at the OH bond that's going to release that proton versus the FH bond that's going to release the proton, O is not as electronegative as F. So this pair of electrons that's holding that hydrogen in place, well, the electrons are shifted towards the O, but not as strongly as the electrons are shifted towards the F, because F is so much more electronegative. So that means the ability of that H to escape is much higher, because it doesn't have nearly the share of that electron pair that the H in the OH bond does. We can say that strengths of binary acids increase from top to bottom in a group. But this isn't because of electronegativity difference. This is because of size. If you think about a fluorine with an H attached to it and a much larger chlorine with an H attached to it, the distance from the center of these two species is much larger with the HCl. And so it's going to be easier for this thing to break away just based on the strength of that bond. And we've looked at the factors that influence the strength of electrostatic attraction. It's the charges, and it's the reciprocal of the square of the distance between the two. So with a bigger atom on the middle, the likelihood of the proton breaking away is higher, and so it'll be stronger. Later we're going to define oxyacids as acids that have hydrogen, oxygen, and another nonmetal. For oxyacids, if they have the same number of oxygen atoms, the central atom that's closest to the top of the group is going to make the strongest acid. And this has to do with electronegativity. Let's look at these two examples, H2SO4 and H2SeO4. I'm going to look only at the chain that's important from the Lewis structure. So this is like a part of a Lewis structure. An SOH chain is going to be present, and this S, of course, is bonded to other things, but we're just interested in this chain. Contrasted with an SeOH part of that chain. For this H to be released, the share that it has of the bond between the O and the H, the share of that electron pair, has got to be low. Sulfur has a fairly high electronegativity. That draws electron share away from the oxygen. But oxygen has pretty high electronegativity as well, and so it's going to fight back by pulling electron share away from hydrogen. That leaves this hydrogen fairly free to break off and ionize. Comparing with SeOH chain, the Se is electronegative, but not as much as sulfur, so it doesn't pull as much electron share away from this pair between the Se and the O. That leaves the O free to share more evenly with the H, and that makes it less likely for this H to break away. And so H2SO4 is the stronger acid because the bond with the H is weaker because the electron share is drawn away. H2SeO4 is the weaker acid because the Se doesn't draw electron share away from the H quite as much due to its lower electronegativity. For the same reason, in oxyacids with the same number of oxygen atoms, the central atom that's farthest to the right makes the strongest acid. So if you think about an SOH chain and a POH chain, the same thing is true. This is more electronegative, so that H is more likely to break away. This is less electronegative, so that H is less likely to break away and makes that a weaker acid. If you have oxyacids that have different numbers of oxygen atoms, the acid that has the greatest number of oxygens will be the strongest. Now this is a little bit harder to understand, but I think the best way to explain it is to look at it from the backward standpoint. Look at it from the standpoint of bases. So this is the anion for H2SO4. It's S, 4 O's, and it's going to carry a 2- charge. For SO3, it's S with 3 O's, and that's also going to carry a 2- charge. Now that 2- charge there is distributed among 4 different O's in the sulfate ion. And so each O has like a -1/2 charge basically attached to it. In the sulfite ion, the SO3, that 2- charge is distributed among only 3 oxygens. So each one of these has got about a 2/3 negative charge. Now if you're a proton out here looking to hook up with one of these two, the one that's most attractive to you is the one that has the most negative charge. And that's your HSO3. So because it's a stronger attractant for H pluses, it's a weaker donator of H pluses. So that makes this a weak acid because it is a stronger base. And then conversely, this would have the weaker base, the less attractive force for H pluses, and that would make it a stronger acid. Let's talk about some other things that we don't normally think about as acids and bases that when you think about it more deeply actually are. Metal oxides react with water and they form bases. These are called basic anhydrides. There's a name for it. An means not, and hydra means water. So a basic anhydride is a not water base. You just add water to it and it becomes a base. So if I have Na2O for an example, and I react this with water, I just put it in the presence of water, it will produce NaOH. Metal oxides are basic anhydrides. Sometimes a metal oxide that won't dissolve in water will function as a base, and then in the presence of an acid, it will dissolve, it will react. Here's a good example. When an acid, an H+, a proton donor, is put in the presence of Fe2O3, the oxygen in the Fe2O3 will accept that proton, and you'll end up with water. And then this will leave you with Fe3+. Now this isn't balanced, but that's what's going on there. Sometimes, when they're dissolved in water, metal ions will attract the negative ends of water molecules and form hydrates, hydrated ions. Aluminum is a good example of this. When aluminum dissolves in water, it'll attract the negative ends of 6 oxygens and create coordinate covalent bonds, and it'll create this complex. The formula for this complex is AlH2O6 3+. That's the formula for this compound. Now, if this metal ion has a great enough charge density, just like other acids, it can draw electron density from that oxygen of one of these waters, and then that will in turn draw electron density away from one of the H's on the water, and that H is more likely to disappear, escape, and become a proton that's loose in solution. So that makes these metal hydrates an acid. But two things have to be true. One is the charge has to be fairly large, so we're seeing like Al3+, and it also has to be small. That's what's meant by charge density. So if you have enough charge density, the metal ion will create this weak acid in this way. So this is with an aluminum hydrate and water. The product is going to be aluminum with only 5 waters complexed, and now there'll be 1 OH complexed, OH minus, for an overall charge of only 2+. And then this will also yield up a proton. So because it donated a proton to the system, it's an acid. So for this to happen, again, it requires high charge density. So the ion has to actually have a small volume, and it has to have a charge. The charge is usually going to be bigger than 2+. Beryllium 2+ is an exception because it's so small. Here's an example. If I have SO3 and I react this with water, I will get H2SO4. If I react carbon dioxide with water, I will get H2CO3, carbonic acid. So by breathing into water, you're actually making the water acidic. So now let's look at acids organized by their structure. Binary acids, as we defined before, contain only hydrogen and one other nonmetal. When we name this, we start the name with hydro and we end the name with ic. So this would be hydrosulfuric acid. The hydro in front means it's binary, so that's how we distinguish this from sulfuric acid, which is a different acid. This one starts with hydro, and in the middle we put fluor, and then we end with ic, hydrofluoric acid. An important class of binary acids is the hydrohalic acids. Halic, you can see, come from the word halogen. So HF, HCl, HBr, and HI are binary acids, hydrohalic acids. Oxyacids contain hydrogen, oxygen, and some other nonmetal. And there is a structural feature of oxyacids. They always have an HO nonmetal chain somewhere in their structure. When we name these, we look at the anion that's present in the acid, And if that anion ends in ate, the acid name will end in ick. If it ends in ite, the acid name will end in us. There's a memory device one of my students invented once upon a time that says ice skate, mouse bite. And built into that is the ick and the ate go together, and the us and the ite go together. So let's look at a couple of examples. H2SO4, this has the sulfate ion in it, so this is sulfuric acid. H2SO3 has the sulfite ion in it, and so it is sulfurous acid. HNO3, nitrate, so the acid is nitric acid. And HNO2 has nitrite in the back of it there, and so this is nitrous acid. And then there's a whole class of organic acids. These are oxyacids that have a backbone of carbon atoms, and it terminates in what's called a carboxyl group. So the generic formula for these organic acids, you've seen this before, is like that, where RC is some carbon chain of some length. And this functional feature here is a carboxyl group. Carboxyl groups are condensed often by writing COOH. So if you see that at the end of a formula like CH3COOH, you know that they're talking about an organic acid or a carboxylic acid. So here's an example. Ethanoic acid, eth you might remember means two carbons. Acetic acid is the common name. So I would draw C, fill that with H's, double bond O, O, H. There's my acetic acid. That's an example of an organic acid. There's that carboxyl group structure on the end. Another one is formic acid, which is methanoic acid. Meth means one, so this is a one carbon acid. So all you have here is the carboxyl group, and there has to be one H attached to it. Well, next time I'm going to talk about something called pH, and basically this is a way of measuring how acidic a solution is by making use of the fact that water is an acid and a base, and it dissociates reversibly to reach a dynamic equilibrium that's very predictable.